alpha helium-3 and
Good afternoon again. Let me thank the organizer for this opportunity. It's really a pleasure to be here. I would like today to talk about the Pandora plasma trap, which essentially step a bit beyond the concept of just a plasma trap, but is also a research facilities for multidisciplinary studies. Will be constructed, and the construction is ongoing at the Southern National Laboratory of INFN in Catania. Before starting, say something about the capability of the facilities and the project, let me just stress some highlights which might turn useful to understand the possibilities, the exciting possibilities opened by these experimental facilities. Let me start from the nucleosynthesis out of the stars. So for the interest of the S and R process nucleosynthesis, I don't spend too much time in explaining this chart, but let me just stress the relevance, just splitting up the arguments both regarding the S process and the R process interest. So as you know, the S process as a universe factory which relies in the AGB stars is a slow neutron capture process, requires a certain amount of neutron density and requires a certain amount of time. So it's interesting to understand more and advance knowledge on the competition between the neutron capture cross-section or the neutron capture rates and the decay rates. As Sergio stressed today morning, if the time scales are closely related, there are many branchings which can change dramatically the backbone of the pattern of the nucleosynthesis process. So there are some open issues, as Sarah yesterday stressed, from the astrophysical models point of view, essentially in trying to reproduce the stellar evolution of such systems, which demands for weak interaction inputs to assess astrophysical models by keeping constant some experimentally assessed quantities, like, for instance, the neutron capture rates. So on the other side, looking at the R process, as already Sergio today morning stressed, one of the possible universe factory are the neutron star merger events. And we are closely looking at these events from 2017 because of the detection of the gravitational wave event connected, correlated also to the electromagnetic counterpart signal, which is known as a kilonova. And there are many uncertainties on the R process yields, which could be somehow constrained by the observation of such kilonova curve, light curve. But for having more information about the kilonova structure, there are some missing pieces of the puzzles, and in particular missing information on the atomic physics inside this ejecta after the coalescence of the binary neutron star system, which might possibly investigated by looking at plasma with the typical conditions of the ejecta at a certain time stage. I will go into the details of these research activities in a couple of slides. So just to focus a bit more in details about the exciting possibilities, one of the first possible cases which might be studied in Pandora regards the change of the decay rate of certain radioisotopes, considering the impact of the strongly ionized environment as in stellar conditions, which is theoretically predicted to strongly impact on the FT values of the decay, which might look a bit different with respect to the terrestrial values. So this is the Fermi theory. Large effects have been experimentally explored already in storage rings. Here reports something back in 1960 about the rhenium 187, which was fully stripped inside the storage ring. And essentially, these radioisotopes was expected to decay in 42 gigayears, but there was a strong reduction of, the decay was much faster, about 9 orders of magnitude faster. And this was interpreted as an effect of the freeing up some K-shell electrons from the atomic support of the nuclear environment, which allows not longer just a free beta decay, emitting the electron in the free continuum, but emitting the electron in a bound states. which essentially change the electron phase space volume and allows to open some forbidden transition, which essentially was predicted by Takashi Oko in the 80s, considering some sort of the perturb theory of the decay rates. So in this sense, there is much more to be explored to assess this theory and eventually, I mean, the other experimental constraints on such a theory by looking at the distribution of charge states and not the bare nucleus like those obtained in storage rings. And in this sense, the beta decay model requires detailed inputs on both the level population, because you have many excited states and many ionized states in a charge state distribution, coming from the plasma supporting essentially the nuclear decay. And you can have essentially here report some equations regarding the FT values enhanced in the stellar environments, not only looking to the continuum decay or the continuum capture, but also on the bound capture and the bound decay. And we need to know some more information about the charge state distribution and the level population of ions, as well as the electron energy distribution functions inside the plasma. On the other side, looking at our process interests, we could have a look on some atomic physics information by studying the magnetoplasma opacity, which comes to be relevant for the kilonova light curve. Why it's so relevant? So, as I said, that there is this electromagnetic signal, for instance, correlated to the gravitational wave event observed in 2017. This is the spectrum observed, which was fitted by a black body function at different stages after the coalescence of the events. The black body looks very nice in reproducing the data. And in particular, people in this community are interested in reproducing some specific spectral features, which in this paper is claimed to belong to the presence of some abundance at this time stages of strontium. So for knowing more about these and to corroborate these aspects, we need to reproduce exactly the kilonova light curve. And among the many ingredients of the recipe, two fundamental inputs comes, which is on the one side, the R process nucleosynthesis yields, which fix the heating rate in the time variation of the energy of the systems. And on the other side, the opacity, which fixes the exchange of energy between the radiation and matter, and is indicative of the amount of energy loss from the ejecta coming from the coalescence. So opacity impacts on the kilonova emission and influence the post-merging plasma ejecta composition. Then in the end, the yields from the R process multi-components modeled by astrophysicists. However, the opacity from theoretical models suffer from a large uncertainty because you can imagine you have the production of freshly synthesized R process elements. There is a plethora of blending of many million atomic transition lines, which is very hard to be disentangled to reconstruct the specific spectral features. So knowing more, I mean, having experimental data, even for the few amounts of elements which are thought to be abundant in a certain time stage, will be of great relevance for the community. Before entering in details of the Pandora, let me just put more information in this community, which perhaps it's not completely aware of what a plasma trap is and what an ECR plasma is. ECR stands for electron cyclotron resonance, which is a mechanism by which we essentially heat some gas which is injected in a vessel, a cylindrical chamber, for instance. This vessel is surrounded by a magnetic field or magnetic structure, which is allowed to produce a magnetic confinement. And taking into account the electron cyclotron frequency of electrons bouncing along the magnetic field lines, if we pump some microwaves at the frequency corresponding to the electron cyclotron frequency, there is a microwave coupling to the electrons, which is quite good, and enhance the heating of the electrons, which ignites the plasma and sustain the plasma itself. The particles, electrons and ions, are continuously trapped inside such a magnetic field, which has a specific topology, which is called the minimum B field, which provides a stable configuration from a magneto-hydrodynamic point of view. And usually this is how ECR ion source appears for accelerators, which was the main purpose of such a system. So you have the trap, the magnetic system, and inside you have this plasma. And then you have an extraction line where there is an analyzing magnet to analyze the output coming from the ion beam currents with, for instance, a Faraday cap. And then it's post-processed in the accelerator lines. So Pandora goes a bit more beyond this. So it's a trap, but is also a research facility. The trap is surrounded by many diagnostics. Here, essentially, are highlighted just a few of them. The hyperpurity germanium detectors for gamma spectroscopy, which is interesting, is actually fundamental to make measurements of the beta decay rate change. I will go into the details in a few slides. But you have a lot of other diagnostics which can independently make measurements of the plasma conditions to assess the reliability of the measurement of interest. So typical density and energy span in this range. And you can see that despite the density is quite low with respect to astrophysical conditions in certain scenarios, at least, the energy span into the energy range of interest for many of the astrophysical scenarios. And in spite, of these, the Pandora concept is to magnetically confine ions of radioisotopes sustained by the ECR mechanism. Among the goals, there is the nuclear beta decay and spectroscopic measurements of in plasma of such ions resembling astrophysical conditions, especially in terms of temperature and ion charge state distributions. So there is a plasma diagnosis system which correlates the experimental measurements to the plasma parameters, and the interest or the possibilities of such facility will span in the interest of a multi-messenger astronomy and nuclear astrophysics because of the typical condition of plasma which can be explored, and for the many aspects that can be possibly explored for many of features interesting for the S process branching, but also for the air process branching. There is the conceptualization of the project required long work. We list a lot of possible physical cases in terms of elements. Here, possibly you cannot see here, but there are more than 120 isotopes. We had to make a choice for day one first cases. And this choice was based on the scientific impact, on the handling of certain radioisotopes for radio safety reasons or for availability of such elements, but also in terms of the magnitude of the stellar enhanced effects which we expected from theoretical expectations. And among these, there are two elements which are of interest, as it was extensively mentioned by Sarah yesterday, but also today by Sergio, on branching process in AGB stars regarding the cesium-134 and the niobium-94. And also another case which is of interest for cosmological reason, the lutetium-176, which is a good thermometer, cosmothermometer. There is still a debate about the capability of use these elements as a cosmochronometers because of an isomeric state of these. But there is a theoretical expectation at the energies we produced in the plasma trap of the reduced lifetime of such elements of many orders of magnitude. And if it is the case, it will be possible to observe in a finite amount of time, days or weeks, this kind of aspects. How does it work? It's a good question. So the requirements for the physical case to be selected is that the beta decaying nuclei needs to decay in daughter nuclei, which then decay by gamma radiation. So in this sense, the gamma tagging of the decay products can be tagged with typical energies which span in 200 keV up to a couple of MeV. So the plasma buffer is a gas, hydrogen, helium, argon, oxygen, neon, and host radioisotopes. This system is kept in dynamic equilibrium for days, even for weeks. And this is based on the peculiar topological configuration of the magnetic field. So the idea is to evaluate the number of decays, which are proportional to the constant decay rate, the density of the isotopes, and the volume of the emitting system, by assuming that a certain amount of these quantities can be kept constant by online monitoring and control of these observables. In particular, the density of the isotopes, which is fluxed inside the systems, and also the plasma volume, which can be monitored by other many diagnoses I will talk about. So the number of decays in this sense becomes linear in time. And if we can be sure that we can measure for a certain amount of time, such as the signal of the gamma decay product overcome the background noise coming from the plasma, because the plasma emits on a quite large range of the electromagnetic spectrum, we can make the measurements. The crucial point is to correlate the plasma parameters to the nuclear lifetime, time by time, second by second. So mastering the stability of the plasma and also control the plasma parameters is a fundamental properties. What I show here is just a study about a typical detection system, which we conceptualize for the measurements. We can use semiconductor detection systems or scintillator systems, but essentially here require hypercuity germanium detector arrays because of the low statistics of these events and the large background coming from the plasma. So despite the efficiency of the two detectors are quite the same, there is a strong difference in the resolutions. And this changes the story in the signal to noise ratio for disentangling the products coming from the plasma emission, the self-emission of the plasma, and the signal coming from the decay radioisotopes. Going to the physics case of the measurement of the plasma opacity, how could we be certain that this can be done in our plasma? We made a feasibility study starting from astrophysical models, trying to reproduce the post-merging ejecta evolution as a function of the density and temperature, and the density as a function of the time after the merger. We essentially constrained a typical density which can be explored in Pandora. The overlap of this box with model results constrained also the typical temperature that can be explored, which corresponds to few electron volts. So the temperature is quite low, staying at these density conditions. This constrains also a typical time stage of the evolution after the coalescence, which corresponds to the so-called blue kilonova stage, meaning that the kilonova light curve peaks at the optical frequencies and it can be explored in the optical range. These again fix another constant, which is the typical composition of the ejecta, which is very low in neutron richness. So we expect a large YE. And according to nuclear network calculations, we select a few elements which could be suitable for day one first cases, going from selenium to rhodium. We also made calculation of synthetic spectra expected for opacity and emission of such elements, a typical density and temperature expected at this time stage, and weighted this with the relative abundance which is expected from the nuclear network calculations. And this is what is shown here in this plot, the product of the two in a log scale. And you can appreciate that these very light elements, despite a low complexity in the atomic shell, shows to be more, let me say, opaque, contributing more in this time stage, and made them quite suitable as elements to be investigated in our plasma facility. How to do this? Well, imagine to have this plasma source. So your plasma is confined inside these magnetic systems. You have a lot of diagnostics here. This is a very complicated figure to look just at once, but I'm sorry for this, but I couldn't manage to split up this in few pieces. You can use an external light source crossing from the outside the plasma, and the photons traveling from the external light source throughout the plasma interact with the matter. So you can make transmittance measurements which are directly proportional to the optical depth of photons inside the plasma, and dependently on the density of the plasma and the typical plasma parameters, you have some proportionality to the opacity of such systems. So by looking at the transmittance by, for instance, optical emission spectroscopy, because we are interested in the optical range, we could try to extrapolate some information on the opacity for fixed plasma conditions and for certain elements which are flux inside the plasma. Of course, there are many challenges coming here because the plasma is not a piece of glass. So it's an active medium, self-emitting, also the frequency which we are exploring. And you have both the buffer gas which sustain the plasma, and on the other side, the elements which is fluxed, vaporized inside the plasma system. So you have to make independent measurements of all the intensity coming out from the plasma. The good news is that our plasma are quite stable compared to other kind of plasmas. So you can reproduce the same kind of plasma even if you switch off and switch on the plasma after even minutes or days. So the bad news is that, as you see, the optical depth is strongly dependent by the density along the line of sight where you detect your light. And also the opacity is a function of the electron density. So you need to make some profilometric measurements of the density along the line of sight. So to reconstruct by inverse processes, the density along the line of sight of your detection systems, to be assured that the quantity that you are detecting is not affected by inhomogeneity of the density along the line of sight, which is actually what happens in our plasma because are strongly inhomogeneous and anisotropic. So let me show you the timeline of the project. So the story goes back to the 2020, as we suffered from the COVID, but we made somehow. We start from the design of the trap because a certain magnetic field has to be required to sustain the confinement of radioisotopes for a certain amount of time to be possibly ionized. And the procurement and the trap design was finished, and also we found in May 2022 a selection of the best technical solution. So the trap is the trap conceptualization and construction is ongoing. Meanwhile, we made some progress from a test bench and experimental point of view on other facilities, most regarding the characterization of plasma trying to reproduce astrophysical conditions of interest for the coronal ejector. And we have a successful test. And also, measurements of X-ray diagnostics and interferopolarimetric diagnostics to reconstruct the shape of a plasma, which is of interest for the reconstruction of the volume of the emitting plasma, which is both space resolved and spectral resolved. We also made in the last months an agreement with the Gamma collaboration to get some high-purity germanium available for the measurements for the test bench, the calibration of the systems, that we foreseen to start in between 2024 and 2025, depending on the availability of the trap and the status of the construction. So, as I said, the magnetic trap is a complex system which comes from the requirement of very high charge state ions. So particle needs to reside inside the system more and more to be stepwise ionized. And for this, high frequency is needed. To get high frequency, this means that you need to get a high magnetic field. The maximum magnetic field, of the system is about 3 Tesla. So you need to go to superconducting coils. You have 3 superconducting coils for the axial confinement and 1 superconducting hexapole for the radial confinement, which provides this minimum V shape of the field. On the other side, we made some progress in virtual experiments to make the ray tracing of the gamma detection to evaluate the efficiency of the gamma detectors array, and evaluate some problems with the signal to noise ratios, which is of relevance since the statistics is quite low, at least theoretically expected. This is a table resuming the plethora of diagnostics, not all, which we in the years master to analyze peculiar features and aspects of the plasma, which could be useful and fundamental for the measurements that we plan. You can extract information both volumetric and space resolved from the soft and X-ray measurements about the plasma conditions, but also the shape and the volume occupied by the plasma. You can extract the average density and temperature by having information from the line ratios of optical emission spectroscopy. But you can make also profilometric measurements of density and temperature by, for instance, using microwave systems which cross the plasma and get information to make inverse profiling reconstruction. And as I said, the plasma emit in a wide range of the electromagnetic spectrum. So all these information are complementary to each other, and nothing can be excluded to have the complete picture. So this is just a nice picture that I have in my mind. Is not a strong statement, but fixing the field of investigation of Pandora. Pandora could make interacting many aspects of the same field, going from theory to experiments and to model simulations, but also to observations, connecting each other by many connection channels. For instance, we used to make use of the outputs for model simulations to design experiments. But at the same time, we made use of the experimental outputs to improve our model simulations in a self-consistent way. And you can see that there are many aspects that are strongly connected to each other, going from theory to model and simulation and experiments, which can be largely explored in this sense. But let me go more in details about the status and the progress of each of these aspects from the PANDORA perspective. Sarah showed yesterday, and also Sergio talked today about the S-only isotope of the barium, the 134, which is strongly which isotopic admixture from the analysis of the silicon carbide presolar grains is strongly affected by fixing some parameters in the models, which are on the one side the nuclear capture cross sections, and on the other side the beta decay rate of such system. By taking into account the reliability of the model and fixing the cross section, the neutron capture cross sections, there is some problem in reproduce the galactic neutron capture, the isotopic admixture of these elements by using, for instance, the Takashi-Okoi predictions for such radioisotopes. But using improved data, which came out from quantum mechanical model, which was developed by Taioli, a collaborator, considering both internuclear and interelectronic interactions, the prediction is that the possible decay rates for this kind of radioisotopes will be a bit slower than was predicted by Takashi-Okoi. And this essentially is the difference between the fitting by using the astrophysical model, the data, by using the Takashi-Okoi predictions, or instead using this work prediction. So it would be interesting to measure and to validate the theoretical predictions or compute. Why not? And this will be possibly done in Pandora. On the other side, there is still a question if, I mean, in astrophysical scenario, often we are in LT conditions, but in our plasma, we are out of the local thermodynamical equilibrium because of the low density. And this could essentially enhance some discrepancies, for instance, in the charge state distributions, which strongly affect not only the atomic support, but can also affect the Q value of the reactions. Because despite beyond the Q0 values, you have many other elements entering in the Q value of the reactions coming from the ion level energy and also the ionization potential depression deriving from the amounts of electrons surrounding the nuclei. So predictions according to the Takashi-Okoi model essentially stress these discrepancies between LT prediction and non-LT predictions at a low density, while of course these converge to the same predictions at high density because the condition out of the local thermodynamical equilibrium is suppressed in this sense. So this also changes the way in which we can have information about detailed atomic physics in plasma, because we cannot use more the Sarah-Boltzmann equation is not a more than statistical approach, but we need to solve the balance equation with direct and inverse process in plasma. We also made some progress on the simulation side. As I said, we used to make a lot of predictions about our plasma systems regarding the electron dynamics and the ion dynamics transport. In this sense, the latter aspects is quite of interest for the studying the space-resolved beta decay emission, according to the fact that the charge state distributions is not homogeneously and uniformly distributed in our plasma, but is distributed according to the physics of our plasma. We also made some virtual experiments to evaluate the measurability of decay rate. We also evaluate the optical properties changes by considering a layered plasma emission, but for this I will kindly invite you to listen to the talk by Matteo later. And we recently made some evaluation about the detection efficiency change of our gamma ray detectors, and in particular the impact of short-lived radioisotopes like the cesium, which has 2 years of the beta decay half-life, coming from the fact that we are interested in the gamma ray signals coming from the ionized radioisotopes and not from the neutrals. Neutrals decay with the terrestrial conditions, ionized not. but these neutrals can decay from the chamber walls and affect the signal to noise ratio. So it's interesting to understand how these can change the efficiency of the detectors and also evaluate the signal to noise ratio in the system. So this is what I mentioned before. On the color bar, there are the charge states for oxygen from 0 to 7 in this case. And you can appreciate that higher the charge state, more closer to the z-axis, to the central axis of the chamber, are the ions. So there is a physics mechanism behind this distribution, but the most relevant things for our purpose is that this means that we have a space resolved charge state distribution, and we expect a space resolved beta decay. This is relevance for the detection purpose. So these are images of the density and the energy density, and they are strongly dependent by the position. This is an effect of the electrodynamics and the ion transport dynamics, but also the magnetostatic field confinement.
Those are simulations, right?
Yes, those are simulations. But we have also experimental data which corroborates, for instance, by looking at the emittance and the extraction of the ion beam current from ion source, that the higher charge states are closer to the central axis region, which corroborates our predictions. So these are measurability of the decay rate. I select here the lutetium case. Essentially, we have some expectation about the variation of the lifetime according, for instance, to the Takashi-Okoi theory, and we can evaluate the amount of counts per second detected by the gamma ray, which is different from the neutral case to the expected lifetime, changing the counts from 10⁻³ to 0.25. So we want to have at least a 3 sigma confidence level in our spectrum. And from this plot, it's possible to retrieve the typical measurability time, the minimum amount of time which we require that the signal overcome the noise coming from the plasma. And for the dilution case, is kind of more than 30 days, so more than 1 month. Whereas for the cesium case is something like 6 hours. So you see that there are strong differences depending on the radioisotopes and the different requirements for detection systems and also for the monitoring of the plasma conditions. This is what the story about the detection efficiency changed by the short-lived radioisotopes. What I simulated essentially is the neutral dynamics in chamber fluxed by the open. This is the inlet spot. The inlet spot is not axisymmetric because of some mechanical constraints, and on the top row you see the no plasma case, whereas considering the presence of plasma, the story changed a lot. So you have a neutral diffusion which homogeneously overcome the entire volume of the plasma chamber, but when you consider the presence of plasma, essentially there are many reactions involved like ionization and charge exchange, which essentially stop the neutrals to deposit on the chamber wall. And we also evaluated the gamma events expected in 12 hours, which is the expected amount of time for the measurement of the cesium. And this is the log scale of the total gamma counts expected in this time. This is very relevant because the array is quite symmetric along the z-axis of the chamber. But in this sense, making some calibration measurements without and with plasma, we have the possibility to unbias the background noise, at least from this source of noise coming from the deposition of the cesium. And this is quite relevant for the short-lived radioisotopes, quite negligible for the long-lived like the lutetium, but it's necessary to evaluate correctly the efficiency of the detection system. We also made some experimental progress, and I will just focus on the measurements we made for the purpose of the opacity measurements. We start from the characterization of the plasma conditions on the flexible plasma trap, which is an ECR trap with different magnetic field configurations and other characteristics, from which it was possible to retrieve the plasma conditions for different configurations of microwave power, microwave frequency, and the gas pressure injected inside the plasma chamber. This is the setup of the experiment. We start from the line ratio method, which is quite known in the optical emission spectroscopy community, by looking at the hydrogen plasma emission combined with a certain amount of argon, which served us to have more constraints on the density profile, on the density estimate of these systems. So the ratio of the Balmer lines, the alpha and beta, for instance, is proportional to the population of this level, but also to the emission coefficients, and these later are function essentially of the density and temperature. So in this sense, you could have a theoretical expectation as a function of density and temperature. You take the experimental values of these line ratios, you combine them, cross the solutions, and you find the observed value of density and temperature, which for some of these experimental configurations, we were able to find desired conditions for the kilonova ejecta, in particular, few electron volt of temperature and 10 to the power of 11 particle per centimeter cube. So we also have the chance to monitor the plasma stability from the emission line ratios. So this is the H alpha over beta ratios for different powers for the many spectra acquired at the fixed configurations. So for instance, at the fixed power and the fixed gas pressure. And you can see that in time is very constant. So stressing the stability of the plasma. So let me go to the conclusion. So many open questions and issues in nuclear physics and astrophysics on both nuclear and extranuclear aspects of key reactions for SR process nucleosynthesis are there. The question is, can you provide experimental nuclear and atomic inputs to advance knowledge on these aspects for the stellar process? And perhaps one of the answers stands in the PANDORA scenarios. We could investigate on the beta decay measurement change in plasma environment, which would have a huge impact on nuclear physics and stellar nucleosynthesis. We could also investigate the atomic physics going on in typical plasma reproducing astrophysical conditions of such ejecta coming from the coalescence of binary neutron stars. And about essentially the timeline, trap and chamber are on construction in the next years. So we expect starting run in 2024, 2025. But meanwhile, we made several progress crossing both theory, numerical simulations, and experiments to corroborate our envisaged picture of the problem. So made a lot of testing diagnostics, design experimental setup, and made the numerical predictions of physics in plasma. This year, we had a chance to publish all the content of these works in many papers in special topics open frontiers. The technical document requirements of the facility is available at this website, and also some other information about the facility and the research tasks are available at the LNS website. So let me thank all the people working in the collaborations without who was be impossible to carry out all this research. So thanks a lot.
So thank you, Angelo, for all of these informations. So some questions?
It's a very impressive setup. It's a really cool idea. Perhaps I missed it. How do you actually inject these beta decaying isotopes in?
Yes. So there are many techniques to inject this. Depends on the elements you want to inject. There are some refractive elements, so that have high fusion temperature, which cannot be vaporized by using a simple open, resistive open. And then you need to use some spattering technique. But the fusion temperature, the evaporation temperature is very low. Let's say, I think under 1000 Kelvin. I think it's possible to use the resistive open to inject vaporized species. Of course, you need to start from some oxide version of the species. For instance, for the lutetium, this is the case, or some solution of the species. For instance, the cesium is expected to use some. Thanks for the light. The cesium is expected to be vaporized using a resistive open by starting from a chlorine solution. Of course, you have some most abundant isotope of the cesium, which is not that one of interest, but we made also calculations of the expected quantity in milligrams, for instance, that we need to use for making the measurement for the amount of time, which is the measurability time for each of the case.
Any other question? So if not, thank you again, Angelo.